Log on, tune in, find out. Another good idea from Cambridge.
Thank you. So I'd like to thank the organizers for the invitation. In this talk, I will talk about D modules on quantized Frag manifolds and representations of quantized enveloping algebras. So I first fix some notation. So G is a connected, simple algebraic group, and German G is German G is the D algebra. And I think I use some standard notation. Q is the root lattice, and P is the weight lattice. P plus is a set of dominant weights. And I denote by U sub Q of G the corresponding quantized enveloping algebra of G. As it is a Hopf algebra, and as an algebra, it is generated by those elements, K lambda, EI, Fi. Here, lambda is an element of the weight lattice. So the Cartan part, I allow the Cartan part, the group algebra of the weight lattice. And it is an algebra over F. F is a field of rational functions. I need this fractional power. M is the order of P over Q. Since I'm considering the group algebra of the weight lattice as a Cartan part. In order to define this algebra, I don't need this fractional power, but in considering the representations, I will need this fractional power. Okay, so I want to consider Frag manifolds corresponding to quantized enveloping algebras, quantized Frag manifolds. So I want to define this. And first I recall the definition of the ordinary Frag manifold. The ordinary Frag manifold for the algebraic group G is defined as G over, this is a Frag manifold, B, G over B minus. And since it is a projective variety, as a variety it is projective, so we can write it as proj of some graded ring. The graded ring is the ring of functions on G over n minus, or the ring of functions on G, which are invariant under the action of n minus. And this algebra, C algebra, becomes a graded ring. In fact, P graded ring. P is the weight lattice. P graded ring. So lambda runs through the set of dominant weights. And the grading is defined by using the action of the maximal torus on G, the left multiplication on G. So in this talk, all graded rings, all graded algebras are P graded rings. So I consider proj for the P graded rings. Okay, so I want to consider the corresponding object in the quantized situation, quantized enveloping algebra. So I imitate this proj construction for the quantized situation. Okay, quantized Frag manifold. So I want to have an analog of this graded ring. And actually, we can define easily the analog of this graded ring. So we have a ring of functions on G, Cg, and there is a natural Q analog of this algebra, Hopf algebra. It is defined as the dual to the quantized enveloping algebra. And we can define naturally a subalgebra of this algebra. and it is a p-graded F algebra. So we can define quantized Frag manifold BQ. I write it as BQ, closure of this p-graded ring. But there is one problem in defining this, since this ring is not a commutative ring. So it is a non-commutative ring. So we need to consider closure of some non-commutative, graded non-commutative ring. So this BQ is a non-commutative algebraic variety, one non-commutative projective scheme with non-commutative homogeneous coordinate algebra. So this is an object in the non-commutative geometry. So this means that I write it as BQ, but we don't have a space or topological space BQ. But what we actually have is a category consisting of quasi-coherent O modules, O BQ modules. I think the main point in defining objects in non-commutative geometry is the following. So in the ordinary case, ordinary commutative scheme is uniquely determined by the category of quasi-coherent OX modules. So this category, from this category we can recover the scheme X. So in the non-commutative setting, we consider some kind of category, abelian category, and we think that we are given some non-commutative variety if we are given some category. So this is the idea of non-commutative algebraic geometry. And in this case, this category is defined as follows. So this is a definition. In the ordinary case, in the ordinary commutative case, the category of quasi-coherent modules on projective variety roughly corresponds to the category of graded modules over the homogeneous coordinate algebra. And so we consider graded modules over this graded modules over this graded algebra. But since this is non-commutative, so we need to fix left or right. I use left modules here. And also in the ordinary commutative setting, the graded modules do not correspond bijectively to the category, do not correspond bijectively to quasi-coherent sheaves. Some graded modules correspond to 0 as a quasi-coherent sheaf. So we need to consider some quotient of the category. And in this case, so we consider something similar in the non-commutative setting also. So I consider torsion modules. Torsion module is a graded module satisfying this condition for any element m. This is killed by CQ G over n minus. If lambda is very large, this is a condition. So anyway, so this defines some category, and we think that we are given some non-commutative algebraic variety. And I also want to consider D modules on this non-commutative variety. And again, we can define the category of D modules on this variety. We don't have actual D modules, but we have a category. So an object of this category may be called a quasi-coherent D modules. And BQ is a Frag manifold. T is a twisting parameter of the ring of differential operators. In the ordinary case, the twisting parameter for twisted differential operators on the Frag manifold, the parameter is given by the dual of the Cartan subalgebra. But in this situation, quantized situation, the twisting parameter is in HF. H is the maximal torus of G, and the F valued points corresponds to twisting parameter. T is equal to 1 corresponds to the non-twisted D modulus. And we can define this category and as follows. So we first define some algebra, dq. dq is a subalgebra of this endomorphism ring of this vector space. So dq is a kind of a ring of differential operators acting on this ring algebra. And it is, as an algebra, this is generated by 3 types of elements. So L of phi, phi is an element of this graded ring. And L of phi is a left multiplication by the element of phi. And we have also a right multiplication, but I don't consider here. I only consider left multiplication. And also, there is a natural action of UQG on this ring, left action. I don't want to define this, but there is a natural action. And also, we have an action of integral weights, kind of grading operator. And so sigma lambda corresponds to left multiplication by a maximal torus on G. In the ordinary situation, this kind of operator can be written in terms of those 2 operators. But I need this in this situation. And also, we have right multiplication of functions, but right multiplication of a function is expressed in terms of those 3 operators. So I don't have to write it. Anyway, so we have a ring of differential operators acting on this ring, but as a of this vector space. And this ring is a p-graded ring, p-graded F algebra, defined from the grading of CQ G over n minus. Now this is dq. dq lambda consists of operator in dq, which sends the degree mu part to degree mu plus lambda part. Okay, so we have some graded ring. And then we can define this category as a quotient of some abelian categories. This category is a category of graded dq modules. And I need some condition about the twisting element t. So I put some condition. Chi lambda is a character of h corresponding to lambda. And since this dq contains CQ G over n minus as a subring, so we can consider torsion modules for the action of this this algebra of functions. Okay, so we have anyway we have a category of D modules, and I want to give an analog of Beilinson-Bernstein correspondence in this situation. And this is given as follows. So this is a parameter of twisting, HF, and we have integral weights, embedding of P into HF. This corresponds to twisted differential operators, and this P corresponds to line bundles. and lambda goes to T lambda, satisfying this condition. And then we have the following equivalence of categories. This is a category of D modules. I denote T is, I assume that T is a dominant weight. And then we have an equivalence of categories. This is a category of D modules. And this is a category of UQG modules with some central character corresponding to T. CT is a central character corresponding to T. We have an equivalence of categories. In this case, the center of UQG is isomorphic to W is a wide group, W invariant elements in the group algebra. Yeah. So this is, and this is an analog of the Beilinson-Bernstein correspondence. Originally, a version of this was conjectured by Luntz-Rosenberg, and I modified the definition of dq, and I proved this theorem. Okay. So far I talked about the case Q is transcendental, and I also want to consider the case Q is a root of unity. So I need some specialization. So F is a field of rational functions, and I consider the subring consisting of Laurent polynomials, and I consider the specialization A to C. Q to 1 over n goes to a primitive Lth root of unity, where L is an odd number greater than 1, and L is prime to 3 for G2, and L is prime to this number, P over Q, the cardinality of P over Q. And since by this condition, so Q to 1 over n goes to a primitive Lth root of unity, but Q also goes to a primitive Lth root of 1. I consider this specialization. Okay, and so we consider several A forms of several objects and consider the specializations. In the case of UQG, there are two A forms. One is the Konchini-Katz form, and another one is Lustig form. The Konchini-Katz form is generated by standard generators as an algebra, and Lustig form is generated by divided powers of the generator. And I can consider specializations at zeta. And both of them are important in this talk. Okay, so I want to consider the quantized Frag manifolds for in this situation. So I need this ring, graded ring. But this graded ring we can easily define using some A forms of CQG, CQn minus G over n minus. CQG is dual to Lustig's specialization of the quantized enveloping algebra. So I can define this. But still, in this situation, this is a non-commutative ring. So we have a non-commutative projective scheme in this situation. So we can define a category, the category of quasi-coherent sheaves on this quantized Frag manifold at zeta in a similar way. I can define this category. But in this case, when Q is a root of unity, we can deal with B zeta in the framework of ordinary geometry, commutative geometry, as follows. I don't have to go to non-commutative geometry in this case, using the following. So I consider the Frobenius morphism or Frobenius twist. So we are considering this this algebra, this Hopf algebra. But in this Hopf algebra, the ordinary algebra, ring of functions on G, is contained in the center of this algebra as a Hopf algebra, Hopf subalgebra. And so correspondingly, we have an embedding of this one. So this is a commutative ring, this is a non-commutative ring, but we have an embedding. And so from this, we can define a Frobenius twist. Frobenius twist. B zeta is a non-commutative projective scheme, but this B is an ordinary scheme, commutative ordinary scheme, G over B minus. And we have a morphism, or we have a finite morphism from non-commutative scheme to a commutative scheme. So using this morphism, we can consider everything in the framework of commutative geometry as follows. So yeah, we taking the direct image using this finite morphism, we obtain some non-commutative algebra. We obtain a sheaf of rings on B, sheaf of all algebras on B, denoted by this one. So this is an actual sheaf of all algebras on the actual space. And we have an equivalence of categories. This category, left-hand side, was defined as an object in the non-commutative geometry. But this is a category of quasi-coherent modules over this ring, over this sheaf of rings on the ordinary Frag manifold. So we can look at this category. Okay. And similarly, we consider the category of D modules on the corresponding quantized Frag manifolds. And then, anyway, we can define this category. No, this category. This category, I define this category, Q as transcendental. But in the case of in the root of unity case, we can also define similarly this category, D modules on the quantized Frag manifold at roots of 1. And the twisting parameter T is in H in this case, HC, H of C. And it is defined as follows. So in defining this, I need some P-graded ring, D zeta. So in defining this, I consider some A form of DQ. I use the DQ for defining this category. But I need some A form and consider specialization. And the A form, this A form, dA, is generated by typical generators, L phi. Phi is, this is some A form of CQ G over N minus. And I consider du. Here, I use the de Contini-Katz form for the part of enveloping algebra, quantized enveloping algebra, and also sigma lambda. So we have some graded ring, P-graded ring, D zeta. Then we can define similarly this category of D modules on this quantized Frag manifolds. The definition is completely similar. But as in the case of O modules, we have an equivalence of category. Or we can replace this category by some other actual abelian category consisting of actual modules on over some algebra. So this is a non-commutative O algebra on the ordinary Frag manifold. So ordinary sheaf of rings on the ordinary Frag manifold. In fact, this should be an algebra, O algebra on the ordinary Frag manifold, and this can be described as follows. So d zeta was a graded ring, so p graded ring, and I consider the part where the grading is L times some element. I took some subalgebra. This is a subalgebra of this d zeta, and then Cp corresponds to the element sigma lambda, and Cp is contained in d zeta 0, so Cp is a subalgebra of this ring, and in fact it is centered inside this algebra, so we can consider the specialization, and we get some algebra, and this algebra is a graded algebra containing this ring as a central graded subalgebra. So this can be regarded as a graded module over this graded ring. So we can consider the corresponding quasi-coherent sheaf on the ordinary Frag manifold. But since this has a multiplication, we can define the multiplication, and this turns out to be an O algebra on G over B. This is just a definition. Okay. And the aim of my talk is the following. So I want to give analogs of results of Bezrukavnikov-Markovich-Reminin about D modules on Frag manifolds in positive characteristics. In the root of unity case, the Q analogs are similar to ordinary objects in positive characteristics. So that's a general phenomenon. So it's natural to pursue some analog of this, the results by PMR using in the framework of quantized Frag manifolds at roots of 1. Okay. So before going to that, I want to recall some main point of the results of Bezrukavnikov-Markovich-Reminin in positive characteristics. So I need some notation. K is an algebraically closed field of characteristic P, and GK is a corresponding algebraic group, simply connected, simple algebraic group over K. And I assume that P is greater than the Cox-Tan number. And I denote by BK the corresponding Frag manifold for GK. And then I have a sheaf of twisted differential operators on BK, dBK lambda. In the ordinary case, the twisting parameter lambda is in the dual of the Cartan subalgebra, H star. For any element lambda, then we can consider some ring of twisted differential operators. And one theorem of BMR is the following. So if lambda is regular, then we have an equivalence of derived categories between the category of D modules and the category of UG modules with some specified central character corresponding to lambda. This is an analog of the Beilinson-Bernstein correspondence in characteristic 0. in the characteristic zero case, we have equivalence of abelian categories if lambda is dominant. But in this situation, in the positive characteristic case, we don't have equivalence of abelian categories. But we have equivalence of derived categories when the parameter lambda is regular. Yeah. And this is one point. And in fact, they proved more in this situation. In the case of characteristic positive, as follows. So this is a ring of differential operators on BK, and in positive characteristics, the center of this ring becomes very large. In fact, the center can be identified with twisted cotangent bundle. The functions on twisted cotangent bundles. If lambda is 0, then this is an ordinary sheaf of differential operators. And in this case, we have a real cotangent bundle. But if we twist by lambda, then we need to consider twisted cotangent bundles. And so we can consider the localization of this ring on this twisted cotangent bundle. We can consider the localization. So d tilde is a sheaf of algebras, O algebras, on the twisted cotangent bundles. And then we have an equivalence of the category of quasi-coherent D modules and the category of quasi-coherent D tilde modules. So we can consider just D tilde modules in this picture. Actually, more precisely, the situation is as follows. So we consider the Frobenius twist. BK is a Frag manifold, and BK1 is a Frobenius twist. And considering the direct image, this is a finite morphism. And considering the direct image, then this is isomorphic to the ring of functions on the twisted cotangent bundles. In fact, the Frobenius twist of the twisted cotangent bundle. So we can consider localization. So the localization of the D tilde is a sheaf on the Frobenius twist of the twisted cotangent bundle. Okay. So using this equivalence, we can just consider D tilde. So we need to know about D tilde. We need to consider D tilde. And we have the following Asmaya property. D tilde is an Asmaya algebra of rank P to twice dimension of BK on the twisted cotangent bundle. This means it is, as an O module, it is locally free of finite rank. And its fiber at any point is isomorphic to the matrix algebra. So the dimension of this is a rank. This is rank. This part is almost trivial. But what Bezrukavnikov Markovich meaning actually proved is the following theorem. I need the moment map. We have a map from the twisted cotangent bundle to the dual of Lie algebra. And they have the following theorem. So if we consider D tilde restricted to the inverse image of the fiber of the moment map, then its it's not only an Asmai algebra, but it's a split Asmai algebra. This means that this sheaf of rings is isomorphic to an endomorphism algebra of some globally defined vector bundle V. And using this, we have a kind of Morita equivalence between the category of D modules supported on this variety and O modules of this variety. In fact, considering the inverse mesh of considering the inverse image, this one corresponds to considering the Frobenius central character of the enveloping algebra. Xi is a parameter for the character of the Frobenius center of the quantized enveloping algebra. Okay, so anyway, they have two main results, and using this, we have a kind of correspondence between some categories. So we have a category of G modules, and we have a category of D modules, and an analog of the Beilinson-Bernstein correspondence, theorem A, gives some correspondence between derived categories of these categories. And this category can be replaced by the category of D tilde modules. And using theorem B, we have some correspondence, kind of Morita equivalence between O modules and D modules, supported on certain subvarieties. And using this correspondence, these correspondences, so we have the following. We obtain the following results, due to BMR. So lambda and Xi. Lambda is roughly the parameter for the character of the Harshchandra center of the enveloping algebra, and Xi is the character of the Frobenius center of the enveloping algebra in positive characters. So specifying lambda and Xi and the number of irreducible modules with specified central character lambda Xi is equal to the dimension of the cohomology ring of the inverse image of the momentum, a kind of Springer fiber. So this is the main point of Bezrukov-Markovich meaning. So now I want to consider some analogs of the two results by Bezrukov-Markovich meaning, theorem A and theorem B, for quantized situation. And I first consider the analog of theorem B about Asmai property, or split Asmai property. So we have the following results. So first of all, I want to consider the center of this algebra. We consider modules over this algebra, but we need to know the center of this algebra. And in this case, the center of this algebra is isomorphic to the ring of functions on some variety, Vt. In the case of D algebras in positive characteristics, we considered twisted cotangent bundles. But in the quantized situation, we have some variety. This plays the role of twisted cotangent bundles. So Vt is a subvariety of B times K. B is a Frag manifold, G over B minus. And K, this K is an algebraic group, algebraic subgroup of b plus times b minus. In fact, K consists of pairs of elements in b plus times b minus, whose Cartan part, torus part, are inverse to each other. This is a subgroup K. And so this K plays the role of the dual of Lie algebra in this situation. The dual of Lie algebra is replaced by some algebraic group K. And we can consider some subvariety. This will play the role of the twisted cotangent band. And phi t is the projection. So we have this isomorphism. In the case of characteristic ordinary situation in characteristic P, then the corresponding result was almost trivial, but in this quantized situation, it's not trivial, so I need some proof. But yeah. But anyway, so this ring, the center of this ring consists of ring of functions on this dt. So we can consider the localization of this algebra on vt. So d tilde is a localization of this algebra on vt. So this is a sheaf of algebras, all algebras on the variety vt. We have some sheaf of rings, and then we wanted to consider this category, but this category can be replaced by the category of d tilde modules on vt. And we have also Asmai properties. So d tilde is an Asmai algebra of rank L to twice dimensional b on vt. This was also trivial in the ordinary case of positive characteristic, but in this situation, it's not obvious. But anyway, so, and yeah, we have a moment map gamma t, and we have the following theorem. An analog of theorem B due to BMR. So d tilde restricted to the fiber of this, the inverse image of a point of the moment map is a split Asmai algebra. Okay, so this was an analog of theorem B. And also, I want to consider some analog of theorem A. Theorem A was equivalence between derived categories. Yeah, I assume that L is greater than the Coxeter number in the following. I'm not so sure whether I really need this condition, but I assume this anyway. And unfortunately, I cannot prove analog of theorem A in this situation. So this is a conjecture, but we have a conjecture corresponding to theorem A, theorem conjecture A prime. If T is regular in some sense, then we have an equivalence of derived categories. We should have an equivalence of derived categories. Between this is a category of d tilde modules, and this is a category of coherent d tilde modules, and this is a category of finitely generated modules over uz of g, the corresponding quantized enveloping algebra. This is the Conchin-Katz form. I consider that the Conchin-Katz form. I should write u sub theta upper dk of g. I forgot. So in this formulation, I consider the Conchin-Katz form. And CT is the corresponding Hartree-Anderson central character. So similar to the case of positive characteristic, we have some correspondence between the modules over u zeta, the Konchini-Katz form, modules over u zeta, and the category of d modules, twisted d modules or twisted d tilde modules. This gives, but this part is conjecture. And by theorem B prime, we have kind of Morita equivalence between the category of d tilde module, some d tilde module, and some O modules on Vt. And if this part is true, we have similar consequence. So if T and K, this part is a central character, Cauchy-Chandra central character, and K corresponds to the Frobenius central character. If we fix Cauchy-Chandra central character and Frobenius central character such that T is regular, then the number of irreducible modules is coincides with the dimension of the cohomology ring of this kind of Springer fiber. Okay. So in the rest of this talk, I'll give some remarks about conjecture A prime. First, conjecture A prime is a consequence of this conjecture 1. Conjecture A prime was about some equivalence of derived categories. But we can prove this equivalence if we have this statement. The global B, this is a sheaf on the ordinary Flach manifold. So taking R gamma, the derived global section functor, and this should be isomorphic to U zeta tensor, some specified central character. This means we have also vanishing of higher cohomology groups. And this implies the equivalence of derived categories. The same argument also already appeared in the work of Bezrukavnikov, Markovich, Ruminin, and I can just follow their argument. And also, there is a stronger version of this conjecture about the finite part. So here I used U zeta, but I replaced it by the finite part, adjoint finite part, U zeta finite. This means adjoint U zeta finite. No, maybe this part I should consider Lustig's form. No. Adjoint to UL zeta of G finite part I should consider. Mistype. I made a mistake. But anyway, so adjoint I should consider the finite part. And we have a version of this for adjoint finite part. And in fact, this is a localization of this subalgebra. So if we have this one, then we can localize this formula to obtain this formula. So the second one is a little bit stronger, maybe much stronger than the first one. But anyway, this implies this one. And also, the second conjecture is equivalent to the following. Conjecture 3. We can consider the induction modules, induction functor. So, from the category of B minus or C zeta B minus comodules to the category of C zeta G comodules, induction functor. And it said that the derived induction, applying the derived induction functor to C zeta B minus. This is an infinite dimensional B minus comodule, C zeta B minus comodule, and with respect to the adjoint action. And this should be isomorphic to this one. This is equivalent conjecture too. So if we can prove this conjecture, then everything is fine. But I don't know how to prove it. But there is a version of this when zeta is equal to 1, or in the ordinary situation for G. So zeta is replaced by 1. So we have a similar conjecture. We have a similar statement. And this statement is equivalent to this geometric statement about the global section of almost some homogeneous. No, this one. And actually, I can prove this statement using some geometry. So this is true. But I don't know whether this is true or not. In order to find the proof of this one, maybe I need some algebraic proof of this fact. But I don't know. Okay. Maybe this is the end of this talk. I give some references. So I wrote 3 papers about this. The first one is about the case when Q is transcendental. And the second one and the third one are about the case when Q is a root of unity. Also, I should mention the work of Bakker and Kremnitzer, closely related work using a different definition of D module on quantized flat manifolds. Okay, thank you.
Thanks very much. Any questions? Yes. Doesn't seem to be the case. Thanks once again. Thanks so much.